Hi everyone, welcome back. Today we're doing climbing stairs, one of the questions for dynamic programming. For this question, we're climbing a staircase and it takes n steps to reach the top. And each time we can climb either one step or two steps. And we have to figure out how many distinct ways we can find to reach the top. In this case, it's a little cryptic, so let's try to visualize this problem pictorially. So let's draw the test case for the first one. So in this case, we have two steps, n is equals to 2. So n equals to 2, and that means you need two levels to reach the top. So in this case, let's take 0 as the ground floor, and this is one step, and this is two step. So this is level 0, level 1, and level 2 over here. So in this case, according to the explanation, there are two ways to reach there. The first way is to take one step and then another step to level 2. The second way is to take one big step and go to level 2 directly. For the second example, let's take a look at this now. Okay, let's draw another staircase. The ground floor, one step, two steps, three steps, 0, 1, 2, 3. And over here, according to the explanation, we have three ways. The first way is to take one step to the first floor, another step to the second floor, and one final step to the third floor. The second way is to take one step to the first floor and take two steps to the third floor. And finally, the final way is to take two steps to the second floor and then take one step to the third floor. As you can see, it's starting to get a little convoluted and it's a little hard to visualize the problem. So one alternative way we can use to visualize this problem is to frame this problem as a graph problem, where if you are on a step, that step itself is a state. And we would try to visualize how many ways we can go from floor 0 to floor 3 in this case. So let's take a look using this example over here. Let's bring it down over here. And let's try to visualize this problem using a decision tree. So let's start off with state 0, where 0 is at the bottom of the staircase. At the bottom of the staircase, we have two options. We can choose to take either one step or we would take two steps. So if we take one step, we will go to floor 1. And if we take two steps, we will go to floor 2. And we will continue this decision tree until we see floor 3. From step 1, we can choose to take one step to go to floor 2, or we can take two steps to go to floor 3. Similarly, if we're at floor 2, we can go to floor 3 by taking one step, or taking one step to go to floor 4. In this case, since 4 is out of bounds, we will ignore that node and we will mark it as ignored later. So at this point, the left subtree looks fine. Let's take a look at the right subtree. In this case, 2, we can take one step to 3, or we can take two steps to 4. And this is pretty much enough, I guess, to visualize the whole problem. In this case, let's mark the out of bounds nodes and ignore them. And let's mark the ways to get to step 3 using green like this. And in this case, using a decision tree, we are successfully able to frame the problem as a graph traversal problem. And you can start to use, in this case, depth first search, I guess, to do this. So at this point, you might be thinking, okay, but what's the drawbacks of this approach? Unfortunately, as you might have noticed, if we take n to be the height of the tree, then the height will be equals to n, where height is equals to 3 in this case. And the time complexity to visit through every single nodes to figure out the number of ways to get to 3, or rather the number of nodes in this case, the time complexity will be equals to O 2 to the power of n. And this is the worst case, average case. It will involve us visiting all 2 to the power of n nodes in this case. So this is very expensive. So one way we can do to reduce the computations we need for this is to somehow reuse the answers that we have in this graph to get the answers for other parts of the graph. For example, if we, as you might have noticed, we can see that there are subgraphs that are copies of each other over here. And to spell it out in human words, this subgraph here represents the number of ways to go from step 2 to step 3. And the solution of step 2 to step 3, number of ways to go from step 2 to step 3, is 1. In this case, since we have 1 tree over here, this would be reused in the other subgraph over here. And if you are using a depth first search traversal where you're visiting the left subtree first, you will end up with the answer over here. And you can cache this, and when you reach this subtree over here, you can reuse that cache, and effectively you have removed the need to evaluate this subgraph over here. You are saving computations by reusing the past smaller subproblem of moving or finding the number of ways to move from state 2 to state 3. So that's pretty much the essence of memoization. This whole process of reusing answers is memoization. And if we memoize this in this case, then effectively the graph that we will really visit is this graph over here. And now our time complexity is pretty much shaved off to approximately ON. So this has saved us a lot of computation. This would be ON time. So we're getting somewhere. So when you do a depth first traversal from 0 down to 3, you would go down this way. You visit 1 node, 2 nodes, 3 nodes, and you also visit 4 nodes, of course. And in this case, after you reach the bottom, you will have to backpropagate the answer. Like if you visit 3, return 1, let's say, and you backpropagate this answer back to the top. So it's a little wasteful to go all the way down from the top to the bottom and from the bottom to the top. So if we know that to get the number of ways to go from step 0 to step 3, we need the smaller subproblem of going from number of ways to go from step 2 to step 3 and going from step 1 to step 3, then why not pre-calculate them first before you proceed to calculate the number of ways for step 0? In other words, why not visit this graph from the bottom instead? So do a bottom-up approach like this. Instead of getting the number of ways to go from step 0 to step 3, figure out the answers to go out, the number of ways to go from step 2 to step 3 first, and then step 1 to step 3, and then proceed to calculate that from step 0 to step 3. And this way, we are saving one full iteration from the top to the bottom. And this would be much more efficient. So, this ON by the way. So, in essence, if we try to reframe this graph over here, let's try to lasso this one and make this smaller in this case. How do I make this smaller? Okay, it's okay. Let's just continue, I guess. Let's carry on here. And let's try to frame this problem as a single array right now, where this is step 0, this is step 1, this is step 2, and this is step 3. So this is not you, sorry. So we start from 3. So as you see from the decision tree, if you're moving from step 3 upwards, then we'll be moving from right to left. So in this case, let's figure out the number of ways to go from step 3 to step 3 first. In this case, there's only one way to go from step 3 to step 3. You're just going to yourself, so that's one way. And in this case, to go from step 2 to step 3, there's only one jump. There's only one valid jump to go from step 2 to step 3, so the answer is 1 as well. And the number of ways to go from step 1 to step 3 would be the summation of the number of ways to go from step 2 to step 3 and from step 1 to step 3. So in this case, this is just pretty much 1 plus 1. So this gives us 2. And to go from 0 to 3, that is pretty much the summation of the number of ways to go from step 1 to step 3 and step 2 to step 3. You can either take one step from 0 to 1 and just reuse the solution of getting from step 1 to step 3, or you take 2 steps to go from 0 to 2 and you reuse the solution of going from number of ways of going from step 2 to step 3. So in this case, this is 3. And one other observation that you might notice is that when we talk about the cache, when you are calculating the answer for number of ways to go from step 1 to step 3, notice that we are using these past 2 solutions here. And similarly, if you are calculating the answer for 0 to 3, you are reusing the answer pretty much only the solutions from step 1 to step 3 and step 2 to step 3. What this means is we can pretty much keep track of 2 variables, and these 2 variables would just be the cache as you try to calculate the ways of going from one step towards like 3, I guess. So that's pretty much it for this solution. And one small little detail that you might notice is that the number of ways to climb stairs pretty much follows the pattern of Fibonacci numbers, where the Fibonacci number is a sequence of numbers where the solution is the sum of 2 numbers before it. So we can see that it's starting to look like a Fibonacci sequence. But that's just a small little detail, and that's pretty much it. Now that we got the approach down, let's try implementing that approach in C++. The first step would be to define the 2 variables used to cache the number of ways to get from one step above us to n and 2 steps above us to n. So let's call this one step above cache. And in the first iteration, sorry, I have to switch from my Python mode to C++ mode. But in this case, this variable over here represents the number of ways to get from one step above to n, to step n. And in the first iteration, let's take a look at the test case over here. So in this case, if n is equal to 3, then the number of possible steps we have is 0, 1, 2, 3. In this case, in the first iteration, the one step above cache over here would represent the number of ways to go from step 2 to step 3. And this, as we discussed earlier, we'll be moving from a bottom-up approach where we would get the number of steps from 3 to 3, 2 to 3, 1 to 3, before we finally solve the final problem, which is the number of ways to get from the bottom of the staircase to the top of the staircase. So in this case, in short, in the first iteration, we'll be starting off with calculating the number of ways to get from step 1 to step 3. And in this case, the one step above cache in this case will refer to the number of ways to get from step 2 to step 3. So this is 1, because the only way to get from step 2 to step 3 is to take one step above. The next is 2 step above cache, and 2 step above cache in this case is also 1. To be specific, this represents the number of ways to get from step 3 to step 3. And you're already at step 3, so the only way to get to step 3 is one way, I guess. So this would represent for n equals to 3, this will be number of ways to get from step 2 to step 3. And the first iteration for n equals to 3, this will be number of ways to get from step 3 to step 3. Afterwards, we'll be doing a for loop iteration to iteratively calculate the solution from getting from step 1 to step 3, and finally the final solution from step 0 to step 3. So we'll be doing in I equals to 0, I less than n minus 1, I plus plus. And in this case, this for loop over here would iterate n minus 1 times. So this makes sense because if you have 3 in this case, then you iterate it twice. And this makes sense because we'll be spending one iteration to calculate the number of ways to get from step 1 to n, or in this case 3, and one final iteration to calculate the final result over here. So inside this iteration over here, our job would be to calculate the number of ways to get from step 1 to step 3. And in this case, how we will do that, we would first define a temp variable, and this temp variable will represent the result in one step above cache first. And once we're done, we would set one step above cache and add it with two steps above cache. This has the final result of adding the number of ways to get from step 2 to step 3 and sum that up with the number of ways to get from step 3 to step 3. And the sum of this would be the number of ways to get from step 1 to step 3. And the reason why we first initialize one step above cache to temp in this case is because in the next step, we want to update our two step above cache to the previous value of one step above cache. So at this point, once we are done, the answer will be stored inside one step above cache. One step above cache will be referring to the number of ways to get from 0 to step 3, or rather n in all values of n. So to convince you that this works, per se I found this quite mind-bending, but let's try tracing this out with a sample test case over here. So n equals to 3. So in the first iteration, one step above cache and two steps above cache will be 1, and this will be 1 in this case. So this refers the answer from step 2 to step 3, and this variable over here represents the number of ways to get from step 3 to step 3. Over here, I will be equals to 0, and now temp will be set to one step above cache that is equals to 1. At this step on line 17, we will add one step above cache with two steps above cache, giving us the answer of the number of ways to get from step 1 to 3. And in this case, one step above cache will be equals to 2. So afterwards, we will set two steps above cache to temp. So in this case, we'll set these to 1. Now we're done with the first iteration. We're finally at the second iteration, which is the last iteration. And in this case, we will set temp to be equals to one step above cache, that is 2. And we will increment one step above cache with two steps above cache. So this will become 3. And two step above cache will now be set to temp. So this will be equals to 2. And we will return the answer 3. And as you can see, this is the same answer as the output over here. So let's run this against some test cases. And this passes, and let's submit this. And that's about it. In this case, as we recap in the explanation before, the time complexity in this case is O(n), and that's because of our act of caching the results for the number of ways from one step to n and two steps above to n. And this saved us the time complexity to O(n). Without dynamic programming or memoization in this case, the time complexity will be 2 to the power of n instead. For space complexity in this case, because we only use two variables to keep track of the cache we need as we propagate the answer from bottom up in this case, then this gives us a space complexity of O(1). We use constant memory for these two variables, and we use constant memory for this variable as well as all of these variables over here. So in this case, the space complexity is O(1), constant. So with that, that's pretty much it for this demonstration. I hope you liked it. If you like this, please give us a like and subscribe, and we will see you in the next video.